So this morning we are going to go through a process where we are going to come up with equations of motion which apply to circular motion. Now, these equations of motion which apply to circular motion, we are going to get them using equations which we already know. Remember, when we're looking at the beginning of the course, when you're looking at description of motion, we came up with how to describe motion in terms of displacement, in terms of velocity, in terms of acceleration. Apart from that, we also came up with certain equations of motions which we have been using. The first one was acceleration A is equals to V minus U divided by T. The second one was V is equals to U plus AT. The third one was, I think, S, which is a displacement, is equals to UT plus half AT squared. Then we came up with something called S is equals to half U plus V multiplied by T. Then eventually there was V squared is equals to U squared plus 2AS. So what we want to do is we want to use those equations to come up with something similar which we can use to describe circular motion. So basically we want to come up with equations of circular motion and uniform accelerated angular motion, because we have seen that it's possible for us to describe circular motion in terms of what is referred to as angular displacement and also angular velocity, and also what's referred to as angular acceleration. Now, the idea of angular acceleration tries to say that it's possible that something can rotate faster than it's rotating. Something can go around a circle faster, but what's more practical is that something can spin faster. For example, your fan can turn faster. If you want your fan to turn faster, it can do that. Or the tires of your car or your bicycle, you can ride your bicycle faster and faster. So the angular velocity of your tires of your bicycle can increase. Or you can drive your car faster and faster until maybe you overspeed and the police catch you, stuff like that. So what is more applicable, especially what is more practical, is that an object can spin or rotate faster and faster on an axis. So acceleration is actually very, very possible. There are other kind of rotations where objects don't really, they rotate with constant velocity. For example, when our planet Earth is going around the sun, it goes around the sun at the same angular velocity. Okay? It doesn't move faster or slow. It doesn't, like this year it's moving faster, next year it's moving slow. It doesn't do that. It moves around the planet around the sun at the same velocity. Also, our planet spins on its axis so that we have got day and night at the same speed. The same thing applies with the sun. The sun also spins on its axis and it rotates around the center of our galaxy at the same speed. So the sun spins, the sun also revolves. Our planet spins and our planet also goes around the sun. These motions, in the case of our planet and the sun, these happen at the same speed. Okay, especially our planet going around the sun. The year is always the same. It always takes the sun the same amount of time to go around. Day and night is always the same. So there is no increase in speed, there is no decrease in angular velocity. But there are certain situations where angular velocity can increase and angular velocity can reduce. So that's what we want to look at. We want to interest ourselves in a situation where there is uniform accelerated angular motion. That's what we want to look at. Now, we already have something to work with. And in the last class, we came up with some relationships which we can use. For example, there is a relationship we came up with which relates the displacement in a straight line, S. S, which is a displacement in a straight line, is related to the angular displacement theta through this relationship. S is equals to r theta. This is what we found out. This is what we saw from our equation of, from the formula. We came up with this expression from the formula for, what is the circumference of a circle. When we divide this expression on both sides by t, we end up with this. You end up with v is equals to r omega. This relationships give, this formula gives us the relationship between velocity in a straight line and the angular velocity. V is equals to r omega. Apart from that, we came up with this relationship. We have this relationship, the acceleration. The acceleration is Venon, can you switch off your microphone? We saw that the acceleration in a straight line, A, is also related to angular acceleration through a similar thing. So all our linear quantities, displacement, linear velocity, linear acceleration, are related to their angular counterparts, angular displacement, angular velocity, and angular acceleration through these expressions. So the rotational counterparts, as you can see, are being multiplied by r, which is a radius of the circular path in which this object is going to move. Apart from these relationships, these three relationships which we have, we can also, using this information which we can derive, we can come up with new formulas to help us describe what's happening. For example, remember in a straight line, when you have in a straight line, there is something called angular average velocity. And average velocity, you can work out average velocity using your initial velocity and your final velocity. So if you know what the initial velocity of an object is, then you know what the final velocity of an object is. If you add up your initial velocity, so here we are denoting the initial velocity as vi, as initial velocity, initial, then vf as velocity final. So if you add up your initial velocity and your final velocity, then you divide the sum of the final velocity and initial velocity by 2, what you get is what is referred to as average velocity. So there is this useful formula which we use to describe how fast things have been moving, average velocity. But with what we know, we can substitute for these velocities, average velocity, final velocity, initial velocity. We can substitute using this expression here. V is equals to r omega. Where there is V, we can put r omega. So if we do that, this side where there is average velocity, we can replace average velocity with r omega average. So r omega average, the r omega average is the average angular velocity. What we are doing is we're simply replacing v with r omega, then we are maintaining the subscripts. So this you end up with, so you're substituting v for r omega, so you end up with r omega average equals to half r omega final plus r omega I. That's what, when you substitute, that's how you do the substitution. After doing the substitution like this, you notice that there is r this side, there is an r inside here. So if you factor out this r and cancel it out, factor out the r and cancel it out, what you remain with is this. You remain with omega average, which is the average angular velocity, is equals to half omega I plus omega f. So this is what you remain with. This expression gives you a way of working out the average angular velocity. Working out the average angular velocity in terms of the initial angular velocity and the final angular velocity. So if you have an object spinning at a certain speed, it has got an initial angular velocity, then this particular object, after a certain amount of time, it begins to spin faster. So you end up having omega f. Then you can use the initial angular velocity and the final angular velocity which this object has. You can use this, you can add them, then you can divide them by 2 for you to obtain what is referred to as the average angular velocity. Are we clear? So that's the first thing you can do. Now, the one thing I want to point out is that as you are doing these substitutions, you will notice that this equation is very similar to this. This is something I'll keep on pointing out. You notice that this equation is very similar to this. What I've simply done is, where there is velocity average, I've written, we now have omega average. The half remains there. This side where you got initial velocity, you have got initial angular velocity plus final velocity, you have got final angular velocity. So you can see that these equations are carbon copies of each other, except that the other one is written in terms of quantities associated with motion in a straight line. The other one is written in terms of quantities which are associated with circular motion. The other thing we can do, now that we know this bit, now that we have this, the other thing we can do is there is this relationship. How much is the displacement? The displacement S is equals to the average velocity multiplied by t. S is equals to the average velocity multiplied by t. We know this relationship from our expression of average velocity, because you can also obtain average velocity by dividing the total displacement divided by how much time it takes you to cover that, say, displacement. So that gives you average velocity. So that is a way of getting average velocity apart from the addition we have done. The additional version, apart from this way, apart from doing this. This is a way of getting average velocity, but you can also get average velocity by dividing the displacement, dividing S by t, that gives you average velocity. So I have written this expression in terms of S. So S, the displacement, is equal to the average velocity multiplied by t. Now, I'll make a substitution which is similar to what we have seen. We know that S, which is a linear displacement, is equals to r theta. So S is equals to r theta, and now we know that V, velocity, is equals to r omega. But now we are talking about average velocity. So average velocity, AV, is going to be equals to r omega average. So when we do this, then when we substitute for S, we put this here. For this S, we put r theta. Then for this bit here, AV, we substitute this bit, r omega average. When we do that, we end up with this. R theta is equals to r omega average t. With this, there is r this side. There's an r there. We can cancel out the r's. When we cancel out the r's, we end up with this. We end up with theta is equals to omega average multiplied by t. Again, if you look at this expression, and you look at this expression, they are carbon copies of each other. It's just as good as for theta, for S, you put theta there. For V, you put omega, then you end up with this. What I'm trying to tell you, what I'm trying to show you is that it is possible for you to come up with equations of circular motion by just substituting the circular counterparts of those equation symbols. As you can see here, things just come out the same. This is the second one, which is coming out similar to the other one. Next, from here, there are other equations of motions which we know. For example, we know Vf, which is the final velocity, is equals to the initial velocity Vi plus alpha t. Sorry, plus at, a being the acceleration. But there are a couple of things we know. We know we can make this up. This is v is equals to r omega, and the acceleration a is equals to r alpha. So if we substitute these, for v we substitute r omega, for a we substitute r alpha in this equation here. So we're going to end up with this side, you're going to end up with r omega f. The subscript remains the same, f. So r omega f equals to r omega I plus r alpha t. There is r this side. If you factor out the r, if you factor out the r, then cancel out, you're going to remain with omega f, which is the final angular velocity, is equals to the initial angular velocity plus alpha, which is the angular acceleration multiplied by time. This equation has the same structure as this. It is as good as where there is Vf, you have replaced omega f. Where there is Vi, you have replaced omega I. Where there is alpha, where there is a here, you have replaced with alpha. The message is the same. You can move between these formulas by just replacing the velocity for the angular velocity, by replacing the acceleration for the angular acceleration. So you can move in between these formulas. Is there a question so far? We can do this because there is a relationship between something spinning or turning, moving in a circle, and moving in a straight line. I've given an example of a car. For a car to move the way it moves in a straight line, the tires have to turn. The amount of turning which the tires are doing is equal to how much distance or how faster the car is going to move. If the tires turn faster, the car moves faster. If the tires are turning slowly, the car moves slower, and it covers less distance. So there is this relationship. These things we are seeing here should not surprise you. The reason is because circular motion is related to straight line motion. There is a relationship between circular motion and straight line motion, which we have seen and which we are using. And basically, circular motion and straight line motion is coming out to be very, very similar. So whatever you know, your reasoning about straight line motion can be extended to circular motion. And there will be a lot more of that coming. Okay. The other equation which we know is this one. S is equals to the ut plus half at squared. Now in this case we are using Vi, which is the initial velocity multiplied by t plus half at squared. Again, we want to find a circular counterpart of this equation. So we have got S, which is a linear displacement. We know the linear displacement S is equal to r theta. Then we have got Vi here. V is the velocity, linear velocity, but we know Vi is equal to r omega I. Then we have got acceleration A, and we know acceleration A is equals to r alpha. This we know, that acceleration A is equals to r alpha. Okay. So if we substitute in here for S, if we substitute this r theta, we end up with r theta equals to, for VI, if we substitute, we end up with r omega I, which is this r omega I t plus half. For A, if we make a substitution for A, we end up with r alpha multiplied by t squared. That again, there is an r throughout, so you can factor out the r and cancel it. Cancelling out the r, you end up with theta is equals to omega it plus half alpha t. You end up with this equation. This equation, theta is equals to omega it plus half alpha t, is exactly this equation. So far things are holding up, and you don't have to memorize the other ones. As long as you know the other ones, you can just substitute for you to get the other equations. So instead of here, for S, you've got theta. For VI, you've got omega I t, then half alpha, then you've got half alpha t squared. Then things are holding up. Other equation of motion, which we know is this one. We wrote it as v squared is equals to u squared plus 2as. But here we have written it as vf squared, the final velocity squared, is equals to the initial velocity squared plus 2as. So we've got the final velocity, we have got the acceleration here, we have got the displacement here. So the substitutions we're going to make are these ones. So for v, we're going to replace with omega f, r omega. For the acceleration, we're going to replace with a r alpha. For the displacement a, so we're going to replace with r theta. So when we substitute for v with r omega, so this side, when we make that substitution, we end up with r omega f squared equals to r omega I squared plus, there's a 2 here, then there's an alpha here, and a, for a acceleration, we're going to replace it with r alpha, which is that r alpha. Then for s, you're going to replace it with r theta. When we square and expand this whole thing, we're going to end up with r squared omega f squared equals to r squared omega I squared plus 2 r squared alpha theta. There is an r squared this side, there's an r squared here, there's an r squared here. So on this side, you can factor out the r squared, then eventually you can cancel out the r squared from the left and the right. When you cancel out the r squared, you end up with omega f squared is equals to omega I squared plus 2 alpha theta. This is what you end up with. You end up with omega f squared is equals to omega I squared, omega f squared is equals to omega I squared plus 2 alpha theta. This is exactly this. Same. So what I'm trying to say here is that they are the equations of linear motion, the equations we use to describe motion in a straight line, and the equations we use to describe motion in a circle are carbon copies of each other. Their structure is the same. You can get the other equations by just substituting what is displacement in circular motion, angular displacement, what is velocity in circular motion, angular velocity, what is acceleration in circular motion, that gives you your angular acceleration. So by making these substitutions, you can get the other things. There are also other physical quantities which we are going to see later, starting next week, probably or that other week, which are related. For example, we have got things like mass. We have looked at things like momentum. We have looked at things like energy and all those things. What are their rotational counterparts? Such things exist. So we are going force. We looked at force, mass, all these things. They have got their own rotational counterpart. Force is in a straight line, but there's something else when you're talking about a circle. When something is moving in a circle, you talk about mass when something is moving in a straight line, but you don't talk about mass when an object is moving in a circle. You talk about some other physical quantity. So there are these physical quantities which we are going to introduce you to, which are copies or rotational counterparts of these physical quantities which you have seen in a straight line. Do we have a question so far? So basically, what we have achieved is the following. The average velocity in a straight line, average velocity is equals to half the initial velocity plus the final velocity. In angular motion or circular motion, average velocity omega AV is equals to half omega I plus omega F. So you can see the formulas are very, very similar. They are basically the same. The displacement S is equals to the average velocity multiplied by the time. The angular displacement theta is equals to the average angular velocity multiplied by the time. This equation, Vf, the final velocity, is equal to the initial velocity plus half AT. This is equal, in the circular part, you have got the final angular velocity is equal to the initial angular velocity plus the angular acceleration multiplied by the time. This equation here, S is equals to Vit, the initial velocity, multiplied by t, plus half AT squared. This side you've got theta is equals to omega it plus half alpha t squared. This here you've got V squared, the final velocity squared is equals to the initial velocity squared plus half AT plus 2as. This side you've got your omega f squared is equals to omega I squared. The final angular velocity squared is equals to the initial angular velocity squared plus half alpha squared. These are carbon copies of each other. You know one, or you memorize one, or I don't know how you're going to do it. You also should be able to get the other ones because you're just replacing circular counterparts of these physical quantities. Is there any question so far? Are we clear? Hello? Are we clear?
Yes, sir.
Okay. So, the message I want everyone to carry home is, since these formulas look the same, they are basically the same, it is very easy for you to describe motion depending on what you want, depending on what's easy. You can describe your motion in terms of a straight line, or you can describe your motion in terms of a circle. You can describe the movement of a car in terms of a straight line, that the car is moving in a straight line. So this is how much distance, this displacement it covered, this was velocity, this is acceleration. Or you can describe the car in terms of what's happening to the tires. How are the tires rotating? What is the angular displacement? What is the angular velocity? What is the angular acceleration of the tires? You can do that. You are still talking about the same thing. So what we have here is we have got two ways of describing the same thing depending on what's easier for you. As some of these examples are going to show, we are going to be moving in between circular motion and linear motion, since you're talking about the same thing. So look at this example which you have here, example number 5. A belt passes over a wheel of radius 25 centimeters as shown in figure 2. If a point on a belt has a speed of 5 meters per second, how fast is the wheel turning? So here we have a fan belt passing over a wheel like in the case of maybe it's in an engine or some kind of engine, simple engine, and this thing, flywheel, has got a radius of 25 centimeters. Any point on this belt, for most of the time, it's moving in a straight line. So there's linear velocity there, but it's connected to this thing which is rotating. So the motion of the belt is connected to the rotation of this wheel here. If a point on this particular surface, on this wheel, on top of this wheel, has a speed of 5 meters per second, that is a V, V is 5 meters per second, then the radius is 25 centimeters, then we can find out how fast this wheel is turning. And how do we do that? Here's a relationship. We know V, the velocity in a straight line, is equals to the radius of whatever is turning multiplied by how fast the wheel is turning. The velocity we have, V, is this one, 5 meters per second, and the radius is 25 centimeters, but this 25 centimeters has to be changed into meters. Then we're looking for how fast the wheel is turning. So we make omega the subject of the formula. When we make omega the subject of the formula, we end up with omega is equals to V divided by R. The V is the velocity, is 5 meters per second. The radius is 25 centimeters, which is 0.25 meters. So if you divide like this, the meters and meters, when you cancel out the meters, you no longer have a unit of distance. The only unit of distance you have now is what's referred to as a radian. So 5 meters divided by 0.25, like this, you end up with 20 radians per second. When you cancel out the meter and the meter, then the radian shows up. So you end up with this. Omega is equals to 20 rads per second. So this is how fast the wheel is turning. We are connecting motion in a straight line to rotational motion using this expression, this formula here. V is equals to R omega. Are we clear? There is always a connection between something moving in a straight line and something turning in different things. Okay. Next, here, a pulley of 5 centimeter radius on a motor is turning at 30 revolutions per second and slows down uniformly to 20 revolutions per second in 2 seconds. Calculate the angular acceleration of the motors. What else are we supposed to do? So the number of revolution it makes in this time, then the length of the belt it winds in this time. So there are a couple of things we have to do here. So we are told this motor, this pulley turns 30 revolutions per second, then it's slowed down. So this is the initial angular velocity, then it's slowed down to 20 revolutions per second in 2 seconds. So this is a slow down. So this pulley slows down. So this is the initial angular velocity. This is a final angular velocity. But these units of revolutions per second, we don't use them in calculations. So you need to change your revolutions per second, you need to change them into radians per second. And the way you do that, the way you change revolutions into radians is by multiplying by 2 pi. So if you multiply 30 revolutions by 2 pi, you end up with this, 188.5 radians per second. Similarly here, the final angular velocity, which is 20 revolutions per second multiplied by 2 pi, you end up with this, 125.7 radians per second. Okay, so we know the initial angular velocity, which is 188.5 radians per second. This is how fast the pulley was rotating initially. Then we know the final angular velocity, which is 125.7 radians per second. You always have to change your revolutions into radians if you're going to do a calculation. I hope that's very clear with everyone. change your revolutions into radians. Then of course the amount of time it took is 2 seconds. So we can work out what the angular acceleration is. Alpha is equals to the final angular velocity minus the initial angular velocity divided by the time. The final angular velocity is 125.7 radians per second. The initial is 188.5 radians per second. So if you substitute here, you have 125.7 radians per second minus 188.5 radians per second divided by 2 seconds. When you do that, you end up with an angular acceleration alpha, which is minus 3.14 rads per second. So this is your angular acceleration in radians per second. So in this particular pulley, in these 2 seconds, it slows down. It loses 3.14 radians per second of rotational motion every second. Are we clear with what you have done? Here, if you're changing revolutions to radians per second, you just multiply by 2 pi. If you're trying to change radians into revolutions, you divide by 2 pi. So since you're changing revolutions into radians, you multiply by 2 pi and you end up with these. Is it clear on how we obtain our angular acceleration? Oh. Let me pause. Okay, so here, what I was saying is that for this example, can you see the presentation?
Yes, sir.
Yes, for this particular example, we need to change these revolutions into radians. The way you change a revolution into a radian is by multiplying by 2 pi radians. So if you do that change, this is what you get. For the initial angular velocity, you get this much. For the final angular velocity, you get this much. And the change in time is what you have here. So when you make these substitutions, the formula for finding angular acceleration, alpha is equals to omega f minus omega I divided by t. So this alpha is going to be 125.7 radians per second minus 188.5 radians per second divided by 2, and you get your angular acceleration alpha as minus 3.14 radians per second. The minus here is telling you that you are losing velocity per second. So there's loss of this velocity which is being lost per second. Is that clear? So that is just a straightforward thing to do. The same way you would do... Yes.
Sir,
Yes, go ahead.
that answer can be correct if you use 2 seconds, unless we use 20 seconds.
What
If you
happened?
use 2 seconds,
Yeah, it's supposed to be 31.4. Yes. Yeah, sorry, it's supposed to be 31.4. So here it's 31.4 here. So similar, I think a similar thing happens this side also. So this is supposed to be 31.4. So similar here, the number of revolutions. So I need to make an edit to this before I do the other classes then. The number of revolutions it makes in this time. So we can also work out how many revolutions have been done in this time. So in this case, I don't know how I'm going to do that. So you have, so the number of revolutions, which is how many times something goes around in a circle, is a measure of displacement, angular displacement. It's a measure of angular displacement. So in that case, we can work out the angular now that we know what the acceleration is, we can work out what the angular displacement is. But you can also make, we can use a different I think you can use a different method. Since we know how much this is, this and this, and we know the amount of time, so we can work out, you can use this. I think since we've got a problem with what we have here, we can try to use this expression here. We can try to use this. Theta is equals to omega average multiplied by t. We can use this in combination with this. So with what we have here, if someone can give us with the calculator how much this is, this plus this, 188.5 plus 125.7, so this is omega I and omega f. We add these, then we divide them by 2. When we divide them by 2, we get these. The average angular velocity. Then after getting the average angular velocity, then we multiply it by 2. That should give us the angular displacement. How much is that? So you have 188.2, 188.5 plus 125.7. How much do you get?
157.1.
Then divide by 2. Okay. Then that is our average angular velocity. Then that average angular velocity, we multiply it by 2, because we have to do this. Theta is equals to average. Theta is equals to average angular velocity multiplied by 2. If you multiply by 2, how much angular displacement do you get? 314.2. Okay, so this thing, I'll have to correct this. So that gives us the angular displacement in radians. Okay, so we can get the angular displacement in radians. Then if you want the number of revolutions, you divide your angular displacement in radians by 2 pi. So I'll need to make a correction to this. You divide the angular displacement in radians by 2 pi, and that should give you how many revolutions. If you divide it by 2 pi, so how much you get? The 314.2 pi, 314 radians divided by 2 pi, how much you get? So
50.006.
50.006. So basically you get 50 revolutions. So I need to make a correction to this as soon as possible before the next class during the evening. Okay, so basically that's how you find out how many times this thing turned during this time. It turned 50 times, 50 revolutions. In that 50 revolutions, the pulley has got a certain amount of length. Radius. The radius is 5 centimeters. So we can work out what is the length of belt it went through. Now, if you're going to work out the length of belt it went through, you have to use your theta in radians, which is 314 radians. So it's going to be 314 radians multiplied by r. So S, the length of belt, S is equals to r theta. So in this case, you're going to have r, which is a radius, 0.05 centimeters, divided by 100, it gives you 0.05 meters. So this is the radius of the belt. So the radius of the pulley multiplied by how many times multiplied by the angular displacement of the pulley, which is how many times in terms of radians per second the pulley turned. So you end up having 0.05 meters times 314 radians per second. How much you get? How much? 15.7 meters. So that's the length of belt which the pulley went through. And if you look at, if some of you have had the chance to look at the engine of a car.
15.7.
Yes, I've heard. So if some of you had a chance to look at the engine of a car, you'll find in the engine of a car, you've got all these pulleys, or engines have got all these pulleys all over the place. And also there are these belts which go around. So basically the belts are there to make sure somewhere the belt is forced to turn, then it turns some other pieces like that. So basically this is something similar to what we are trying to discuss here. How much length of belt is 15.7 and stuff like that. Okay, so I think here the small amount, I think it's either, in this example, like the other student has said, I make this 20 seconds. If I make it 20 seconds, then I don't have to change a lot. I only need to change here, then everything else remains the same. I think that's a better way than doing everything else. So I will just change, in the example, I'll just change it to 20 seconds, then everything else should remain the same so that I don't have to do a lot of work myself. I don't have to do a lot of corrections. So let's just assume that, I think, 20 seconds. If all this thing happens in 20 seconds, then fine, then everything else comes out as it's supposed to do. I think that's a much better option for me. Okay. Any questions? So here we have an example where something was rotating, then we translated it into how much distance the belt actually moved. Example number 7 is actually something which moves in a straight line, I think. Then we try to, in terms of straight line, then we're going to start with linear, then we turn the linear things into circular stuff. So 7, a car has wheels of radius 30 centimeters. Now, I must say this radius of 30 centimeters, unless maybe it's a very, very big thing. But usually typical radiuses of cars' wheels are 14, 15, 17. But fine. 30 centimeters. It starts from rest and accelerates uniformly to a speed of 15 meters per second in a time of 8 seconds. Find the angular acceleration of its wheels and the number of rotations one wheel makes in this time. So, this is exactly what I've been saying. To say, as much as a car is moving in a straight line, that's fine. But for a car to move in a straight line, it needs its wheels to turn. So, we have a car which starts from rest, and it increases its velocity to 15 meters per second in a time of 8 seconds. So with this information, we know that since it's starting from rest, the initial velocity u is 0 meters per second, the final velocity v is 15 meters per second, the amount of time t is 8 seconds. With this information, we can work out what the acceleration is. The acceleration a is equals to v minus u divided by t. So in this case, we're going to end up with a is equals to 15 meters per second minus 0 meters per second divided by 8 seconds, and we're going to get an acceleration of 1.9 meters per second squared. So this part is straightforward. What you are being asked, this acceleration you found is acceleration of the car in a straight line. What you are being asked to find is the angular acceleration of the wheels. Because for this thing to happen, the wheels have to turn faster and faster and faster. So the question is, how fast are the wheels turning during this time? So we have the relationship A, linear acceleration is equals to r multiplied by angular acceleration. So what you're looking for is the angular acceleration alpha. So we make alpha the subject of the formula, we end up with alpha is equals to A divided by R. So if we do that, so you end up with alpha is equals to 1.9 meters per second divided by the radius. This radius of 30 centimeters has to be changed into meters. You end up with 0.3 meters. So you have 1.9 meters per second divided by 0.3 meters, and this is going to give you an alpha which is equals to 6.3 radians per second squared. This is going to be acceleration. Are we clear? This is going to be your angular acceleration. Yes.
When you divide 1.9 meter per second squared with 0.0 meter, the meter and the meter is cancelling out, and you are remaining with only second squared.
So when the meter and meter disappear, that's when the radian shows up. So in place of the meter, then the radian surfaces. Yeah. So you end up with having acceleration alpha, which is equals to not 3. You don't write it as 6.3 per second, but you write it as 6.3 radians per second. If you multiply something with a radian with a meter, because the radian and the meter are both units of some kind of distance. The meter is a unit for linear distance. The radian is the unit for angular displacement. So when the radian and the meter, when you're multiplying and they meet, then the radian is going to disappear. But if you are doing a division like this, then the meter you divide, then the meter cancels out, then what you're going to remain with is a radian. Okay, any other question? Okay, thank you very much. Then there's another question which says the number of rotations the wheel makes in one time. The number of rotations is a measure of angular displacement. What is the angular displacement? But you're measuring the angular displacement in terms of rotations or in terms of revolutions. Remember, angular displacement can be measured in terms of radians, it can be measured in terms of degrees, it can be measured in terms of revolutions. So in this case, for us to find out what the displacement is, angular displacement, we can first of all find out how much distance was covered by this car in this 8 seconds. We have a way of doing that. S is equals to half u plus v multiplied by t. So this is a quick way of estimating what the distance is. So in this case, we've got s is equals to half. The initial velocity is 0 meters per second. The final velocity is 15 meters per second, and the amount of time is 8 seconds. So this is going to be end up with half 15 times 8, and we end up with 60 meters. So in this time, in this 8 seconds, the car covers a distance of 60 meters. If the car covers a distance of 60 meters, and the radius, and this car has got a wheel with a radius of 30 centimeters, then we can use this formula here. There's a formula we came up with. We have, where is that? S is equals to r theta. We can use the expression formula S is equals to r theta. If you remember very well, S is equals to r theta, then you make theta the subject of the formula, you're going to end up with theta is equals to S divided by r. This is one of the first formulas we came up with when we started out the course. This topic. So you end up with theta is equals to 60 meters, which is the distance which has been covered in a straight line, divided by 0.3 meters, which is the which is the radius of the wheel. When you do this, you end up with an angular displacement theta, which is equals to 200 radians, like that. Now, this is the angular displacement in radians, but the question is asking us to find out how many rotations does the wheel make. So we have to divide. For us to get the number of revolutions, we need to divide our radians by 2 pi. So when you do that, you do the division. So it's going to be 200 radians divided by 2 pi, you're going to end up with 31.8 revolutions. So basically, roughly, the wheel is going to turn 31.8, basically it's going to turn 32 times, because it's more than 31 times. So approximately, this wheel is going to turn 32 times. Is this clear to everyone?
Yes, sir. Yeah.
Use the example of a car. The car moves, it covers distance in a straight line, but for a car to do that, it needs the tires to turn. So your tires have to turn a certain amount of time. The faster the car moves, the faster the wheel turns. So if the car moves, if your car undergoes acceleration, the wheels are also undergoing acceleration. If your car covers a certain amount of distance, your wheels are also turning a certain number of times. There is a connection in this case. When we use examples of cars, there's a connection between distance in a straight line or motion in a straight line and circular motion. And that is what we wanted to show you today. Are there any questions? Is it clear?
I have a question.
Yes.
I've seen one link for group O on motor showing that the class should start.
Sorry? Group,
I've seen a link
yes.
showing group O having a class on Saturday.
No. That was supposed to be a makeup class. I'll delete that link.
Alright.
That was supposed to be a makeup class some time back. I'll have to delete that link. So group O meets on Monday, 14 hours to 15, and we meet this morning, 8 hours to 9. So we are done with this bit. So the next time we're going to meet on Monday, we're going to talk about something called centripetal acceleration and also something called centripetal force. That will be on Monday. Then after that, if some of you have been checking Moodle, we have notes for the next topic: rotational work, energy, and momentum. So download those notes, print them out, study them, so that if there's a bit you don't understand, when we start meeting probably on Thursday next week we'll start rotational work and energy, and momentum. So print the notes, study them. Okay, so that you can ask. If you don't want to, you can write the notes yourself, but it's a lot of work writing the notes yourself. Okay, so we are, any other question? Unless there's another question?
Is simple harmonic motion part of our syllabus?
Simple harmonic motion. Yes, simple harmonic motion comes, but simple harmonic motion comes later. Simple harmonic motion is a special type of motion which we use to describe waves. So waves later on, I think probably sometime in August, or somewhere there. August or September. That's when we'll be looking at waves. I think so. But yes, it's part of the syllabus.
Alright.
Yes. Any other questions? Okay, if there are no questions, we'll stop here. Have a good weekend. Take good care of yourself. The COVID is not over. Okay? And wear a mask. So the recorded video is going to be uploaded to YouTube, and the link is going to be shared on Moodle as usual. Alright, so see you on Monday.